Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today we're going to talk about how to evaluate fin stabilizer performance in your ship motion analysis project in ProteusDS. This is particularly useful in early stage design when you're just trying to get a sense of what might be possible from these kinds of technologies. So what we're going to use is the 50-meter generic yacht to play with and take a look at and get a feel for how this works. You can see that I've added some 3-meter square area fins, kind of at the maximum beam position. I wouldn't always necessarily say that's the best thing to do, but it's very simple, and it just illustrates a few things I want to highlight for the moment. So we've added these fins. And you might be wondering, like, well, how do I know how much better the performance of the ship is going to be? And there's a few ways we can do this. The first thing we do is look at the roll RAO. So you can evaluate that using the ProteusDS ShipMo3D toolset Seakeep Regular app. So what we want to do is look at Seakeep Regular, and what I've got set up here is the bare hull analysis. So this is analysis without fins. And we'll run this, and it always helps to get a basis for comparison, right? So we're going to look at the 12 knot speed condition, and the reason for that is that the viscous forces on the fins are evaluated with the forward speed condition. So that's in the software right now, so that's the best way to kind of get a picture of what they're going to do. So for the bare hull, we look at 12 knots forward speed and 90-degree beam condition. Of course, we've got a very nice strong roll resonance effect happening here. And then pay attention to how the roll RAO is non-dimensionalized. Different programs non-dimensionalize roll motions, pitch motions, yaw motions differently. This is non-dimensionalized by the wave slope, so it doesn't have units. It's basically a value of 11. So that's a pretty high roll RAO value. So we'll go back to this and then pick our case with fin stabilizers in midships, and we'll run that, and we'll go plot motion RAO, look at the 12 knots case, 90 degrees condition, and you see the sort of peak roll is sort of 1.2, 1.3. You know, it's almost an order of magnitude lower roll motion. So this is like really encouraging to see just like a dramatic improvements. You know, that's going to be the best case scenario because that's in beam conditions when it's, you know, hitting the ship on the side and seeing what's happening there. But, you know, just good to get a quantifiable look at what it could be. So the next step that you want to do is look at what happens in some kind of representative sea state. So you can do that in Seakeep Random. So we'll jump over here, and this is different than Seakeep Regular because in Seakeep Regular you're just looking at sinusoidal waves, individual frequencies. This is looking at a sea state spectrum. So I've got this set up with 1.5 meter significant wave height, 7.5 peak period second John swap. And first we're going to look at the bare hull response in these conditions. So we'll run this, and just takes a second, and we'll look at plotting the motion RMS. So again, we'll look at the 12 knot condition, and we're looking at a C direction 90 degrees. That's the beam condition. You know, the bare hull is looking like an RMS value of 8.3, so that's kind of the average roll, you know, kind of thing. Of course, it's going to potentially in a regular sea state can have bigger maximums, but this is giving you an idea of how much there is. And then, of course, we want to see how that changes with a fin configuration. So we'll pick our midships configuration here and run it. And, you know, what we're trying to do is just make a comparison to see how much the RMS rolls changed. So we'll plot motion RMS again, look at the 12 knot condition, and then in 90 degrees, you can see that we're like 1.6 degrees RMS roll. That's, you know, significantly less than 8.3. It's not 10 times, but boy, it sure is a big reduction. Another thing to keep in mind also is to look at that fin stabilizer RMS value. So remember, there's no stall effect included in these hydrodynamics calculations, so you kind of want to be avoiding having too high of a fin RMS value. And, you know, it just might mean it's time to, if you get too big a fin RMS, maybe it's time to be using bigger fin areas, but that's another story. Anyway, we're getting promising improvements in an individual sea state and also in the roll RAO. And what's the last thing that we can do? This is where the Ship Motion toolbox comes into play. And what I've done here is I've got the Ship Motion toolbox here. and we're going to do a comfort analysis. Here we have all of the areas set up for the generic 50 meter yacht hull. We have the bare hull already computed, and I've got a few cases here. So this is the bare hull. Here we have an overall comfort rating of 51%, and then we have the fin configuration that we were looking at, and we got an improvement in the overall comfort rating. You can zero in on the forward speed condition and kind of get some insight into like what's going on and how are things improving. Generally speaking, in this case, there's some motion sickness incidence cases you can't do too much about. And then we do see some improvements. So this is the bare hull. There's lots of conditions going over the criteria, and the fin stabilizers you can see are helping a lot with that. So again, just helping show that you're moving in the right direction with your design. So summarizing the three things you look at: roll RAO, that's the first, quickest, easiest way to kind of get an idea of how the stabilizers are helping. Then look at a representative sea state. We were looking at 1.5 meter, 7.5 seconds to see how that's improving things. And then of course with an operability analysis in the ProteusDS Ship Motion toolset, we're looking at the comfort rating here for the ISO standard for large yachts. That gives an indication of how things are improving. All right, that's all for now. Thanks for watching.